All right, so welcome to this tutorial. I tried to really start from the base. I'm gonna cover a few concepts about ORAN E2 interface, E2 agent, E2AP, RIG, and also the xApp. And then I also present you one implementation that we did in the context of open air interface. So if we really go back to the software-defined networking, SDN, right? Everything is started from SDN. So essentially what we have is that in the wired network, we had a bunch of switches, right? Originally, they were distributed, right? What we did is that we make it more centralized by having the user plane, like packet processing, packet forwarding on the switches. But the decision-making process is offloaded to a centralized controller that you see here. So essentially, these switches have a southbound to the controller, and the controller has a northbound to the application, essentially allowing the application to program the switches via the controller. I think this concept was like a middleware. Back then, we had some concept of the middleware. So controller are kind of a middleware in this sense. So central controller with a network-wide view. So from the controller, you can get the network topology, the whole topology. You can make centralized routing or networking decisions. So for each switch, for each flow, you can make a decision. You have a programmability because of the northbound, right? You can actually have some logic here through which you can control the switches. So the protocol, the language from the application to the controller is different from the controller to the switches. Two different languages, two different protocols, completely different. And one standard was OpenFlow. Probably you have heard about OpenFlow. So OpenFlow was kind of the first protocol implementing the southbound, not the northbound. So the southbound between the controller and the switch through which you can program the switches. So that was the concept of the SDN that originally introduced. Now we try to understand what is the software-defined radio access network and how it differs from the SDN itself. Because we actually, wireless guys, we borrowed the concept of SDN and we brought it into radio. So let's first focus here and then I go to the bullet points. If you have, let's say, if you have a cellular system or 4G or 5G that are deployed and you have no sharing and you don't really want to do anything, you don't want to program anything, in that sense, you have kind of a dedicated radio access network. So it means that you deployed the base station as a black box. It is dedicated for particular operator. No changes can be actually made here. On the other side of the spectrum, you could say, okay, I'm 100%, I want to share my RAN, like more RAN, multi-operator RAN, which is allowing to share the radio access network along the operator. So here you have a full sharing. So the operator, they can share the spectrum, but there is no isolation. So operator number one cannot say my infrastructure is isolated from operator number two, or my radio resources are isolated from operator two. So it is still not a good solution because operator, they want to have also the isolation. So if I have certain spectrum, maybe I don't want to share it with anyone. Like for instance, for public safety application is like that. You don't want really to share. Then there is this concept of RAN sharing, a slicing that came to the picture to share the RAN while doing some isolation. And on the other side, you also have this infrastructure sharing. So you want to also share the infrastructure. So essentially, SD-RAN came as a natural solution to address this 3GPP multi-operator radio access network for sharing. And then new requirement came to the picture along the lines. So one of the difference between SD-RAN and SDN is that the base stations cause interference and you need a coordination. So you need to coordinate across many base stations to make sure that your users get the performance they deserve, or even you can make sure that the right part of the spectrum is allocated to the right part of the operator. Another difficulties in SD-RAN is that as opposed to the 4G, the 5G is disaggregated. So all of you know you have CU and DU, that is one dimension, but even the associations, the relationship between CU and DU is not one-to-one. So one CU could have many DUs, right? And CU also, CU-CP and CU-UP, there is also one-to-many association. So a base station is disaggregated into 3 entities. And from the SD-RAN controller, you need to program one logical base station. That is composition of many logical entities, right? So it makes it more sophisticated to actually merge the information from 3 elements and make it programmable by the application. Another fancy features of SD-RAN that we are looking is that one is to make sure that we can manage the traffic flows like we are doing in switches. Like switches, you are actually managing data flows. You're doing packet processing. So this is a missing pieces in wireless. So you want to do the flow processing, traffic control, and this happens at the CU. And you have a high frequency resource allocation, probably sub-millisecond, right? That you want to also control from this SD-RAN. So these are the difficulties of the time scale that you have in SD-RAN that you don't have in the SDN switches. So the time scale could be, as I said, in a sub-millisecond level. So SD-RAN borrows the concept from SDN, but it's not the same thing. It's fundamentally it's different. Okay, when we look at the O-RAN architecture, so O-RAN architecture from the beginning considers disaggregated RAN. Here you see you have a CU-CP. So this is the centralized unit control plane. CU-UP, which is the user plane, and then you have a DU. Here, you don't really see the relationship. You know, for instance, one CP or one UP could have many DUs, or one CU-CP can have many CU-UPs. You don't see all this relationship, but there exists, right? So there is this interface E2 that you see E2DU and E2UP and E2CP that goes to the near real-time RIC. RIC stands for RAN Intelligent Controller. So this E2 is one of the interface standardized by O-RAN, which is a very generic specification, which is vendor neutral. It means that the vendors, they can define their own service model, but this protocol, E2AP, is completely vendor neutral, right? And then on the top of near real-time RIC, you have also non-real-time RIC, which is a problem of the time scale. If you want to do, for instance, resource allocation type of control, you probably need this near real-time RIC. But if you want to do some handover or something that is of the higher order of the time, you can go to this non-real-time RIC. It doesn't mean that those operations cannot be done in the near real-time RIC as well. So one of the shortcomings of this architecture is that it does not consider real-time operation as well. If you want to go to 6G, you have some beamforming, some sophisticated mechanism that you need sub-millisecond granularity. The specification does not allow you to reach that. The order of magnitude here is 10 milliseconds. Yeah, so if we go forward, so there is a bunch of terminology. Unfortunately, you need to learn them. Let's first look at on the right figure, and then we go to the terminology. On the right, what we see is that we have an E2 node. So this is a generic term that could be CU, DU, no matter which entity. So E2 node is just the logical entity that could be any entity in 5G. Inside the E2 node, you have an E2 agent. So this is the agent that is actually in charge of interacting with the run function. So you see function one, function, and these are the run functions. So for instance, you could have one run function for the handover, one run function for resource allocation, and one run function for just monitoring, right? And then on the rig part, you have the E2 termination. So this E2 termination, you see that here there is a E2 protocol, E2 termination, and you see that actually there are two lines. One is the black, the other is red. The black is the E2AP protocol, which is vendor neutral. So E2AP is the protocol that connects the rig to E2 node. The same procedures as in 3GPP, like E2 setup request, E2 setup response. It's exactly the same type of protocol specification. However, the red one is more interesting. Red one is vendor specific. ORAN specifies their own service models, but each vendor, they can define their own red lines, which means that, okay, I define my own service model and I connect my X application to the function. So essentially you have two protocol embedded, like GTP and IP. You have E2AP protocol, that is the protocol that encapsulates the other protocol for the service model, which is the red one. So run functions are those that are controlled by the xAPP. So xAPP, they use E2AP protocol to control the run function. Imagine your run function is a MAC scheduling. The xAPP here is gonna control that specific run function. Another example, your run function is just monitoring, right? So your xAPP here is a consumer. It's just receiving the monitoring information, post-processing or pre-processing, and generating whatever it requires to be done. It could be machine learning, it could be visualization, it could be anything actually. So E2, which you see, is the interface between the run and the read. If you go to the terminology. E2AP protocol is the E2 management and service encapsulation. So you have the services that are supported are report, control, insert, and policy. These are the four services that RIC provides to the xAPP. So one xAPP would say, I want a report. Give me the monitoring. I want to control. I want to perform a handover. This is a control. So read and write is like a control and the report. Insert is very interesting. Insert, it means that you inject a logic into the control plane of the RAN. For instance, in the RRC connection procedures, you want to interfere. You want to, in the handover procedures, you want to interfere. So you don't allow the RAN to decide by itself, but you inject a control logic inside the control plane, right? And policy is that you inject some policy. E2 agent is this entity that actually managing the E2 connection, E2AP. Run function is the functionality that you want to control via xAPP, and they are encapsulated through E2SM, E2 service model. And this E2 service model, it is the red line, allowing the xAPP to control or monitor the run function. RIC service messages. So RIC defines some service messages. And as we said, RIC service, we have 4 RIC services: report, control, insert, and policy, we will see. And xAPP is actually the end user logic. Whatever that logic it is the end user logic. Okay. If we go a bit into detail, the E2 interface, so the one that is vendor neutral, is composed of the RIC services, E2AP procedures, and E2AP information element. So these are the 3 things we have inside the E2 interface. There are 4 RIC services, as I said, and you're gonna actually see it. We have a report, insert, control, and policy that we discussed before. There exist 26 E2AP procedures. For instance, E2 setup request, E2 setup response, 2 of them, right? We have 26 of these procedures, which these procedures has nothing to do with the xAPPs. This is really about the E2AP protocol. So 10 messages are for near real-time rig functionality, and 16 messages are global procedures that you see, setup request and so forth. And there are also information elements like global rig ID, rig indication header, and so. So this is more about how the protocol is designed, and it's very similar to what RRC is specified. All right, let's see, for instance, a setup request. So you have the E2 node. So imagine that you have a disaggregated base station. From the rig, you need to do 2 times E2 setup requests, one to the CU, one to the DU. And then the rig needs to merge this information into one logical entity, right? So you have E2, first you have a SCTP connection that you see. The SCTP connection must be established. This is what 3GPP actually is using. Then the E2 node initiates E2 setup request. So E2 setup request has a lot of information like rig global ID, and then you receive the E2 setup response back to the E2 node. So this means that the rig and E2 node are connected. They know each other. For instance, they know the identity of the base station, the P element, and also what is very important, through this process, the rig also understands what are the RAN functions available inside the agent. Because rig, you can imagine that you have many base stations, each of them have different RAN functions. The base station 1, RAN function 1 and 2, base station 2, RAN function 3 and 4. So through this process, the rig knows what are the supported RAN functions, right? So you cannot perform illegal operation. This is another process. So this is the rig service, a rig report procedure. So here, first thing to do is that you need to subscribe, right? You need to subscribe. So there is this rig subscription procedure that through which you subscribe to E2 node. You subscribe, for instance, for the MAC statistic. You subscribe for RLC statistic. And once the statistics are available, the RAN function will trigger and will send you the rig indication, which essentially is a report. Report is, for instance, RLC monitoring or MAC monitoring. So this report procedure is essentially used for read operation. You monitor anything you want, right? You take open air interface, you implement monitoring of, let's say, STAP layer, right? You encapsulate in a service model, and then through the indication, you send it to the xAPP, right? You don't need to touch E2AP. E2AP is already, for instance, done. And then this is a control. The control is more sophisticated. So in the control, you have some rig internal messages. What will happen is that you send a rig control request. So you have some actions to do. For instance, in OI workshop, we showed, for instance, a slicing or traffic control. So once you make a decision through the xAPP, you send this information to the rig. Rig will do a rig control request for you to the E2 node. It comes here. Then the right RAN function is called, and then you have the acknowledgement or the failure of the control, depending on whether it was successful outcome or unsuccessful outcome. Okay, and here I put, let's say, the recap of everything. So what you need to understand, the most important things from the xAPP perspective is not E2, but it is E2SM, E2 service model. You have 4 rig services for the xAPPs that are very important. Report in charge of monitoring. For report, you need to first subscribe. Once you subscribe, you receive the indication. You need to subscribe to a RAN function, right? Subscribe to RAN function number 1, RAN function number 2, and you receive the indication from that RAN function. You have the insert. So insert, again, you need to subscribe. And subscription, you have a type insert that you see here, and then indication with the insert. You have a control, and you have the policy. And here subscription, you inject the policy, and then you have the acknowledgement. And then the policy, for instance, is performed here. And again, rig services are the red lines, is not a black one. So it's directly between the xApp and the run function. So in summary, the E2 interface is composed by services, procedures, and information elements. So the services have many procedures, and each procedure has many information elements. And information element, they have a lot of types on and valid ranges. So now there is also E2AP version 2.0 that is actually released. So this has been a new release in E2AP, but essentially it's very similar to the old version. So now we try to look a little bit deeper into service model. I don't want to take too much time here because it's too much detail, but it is still worth mentioning the service model, because this is essentially where it is vendor specific or user specific. You need to define your own service model or implement the standard service model that ORAN specifies. So they have one which is KPM, key performance monitoring. They have RAN control, network interface, hello world. So they already defined a few standardized service model. So, a service model is a description of the service exposed by a specific RAN function. So as long as you implement a RAN function that does something, you can expose the functionality of that RAN function through the service model. You can actually encapsulate those functionality by means of a data structure, to put it very, very simple. And that service model is encapsulated into a E2AP. So you have two encapsulation. One is the E2AP, the other one is E2SM. It's like E2AP has a container for E2SM. So E2 interface is used to carry message between a given RAN function and the near real-time rig. So E2AP is just a transport protocol for the service model, right? So E2AP has no value rather than connecting rig to E2 agent. The real value is a service model. So these messages are RAN function specific and are described in a corresponding RAN function. So essentially, you need to understand that most probably each E2 node, like CU and DU, they have different set of RAN functions, right? And for each of them, you have different service models because they are not the same. So here it's taken from standard. So you have RAN function. So in E2AP, there are many specific procedures for this RAN function. For instance, rig action definition or rig indication header, rig indication message, or rig control header. So you remember that I mentioned we have 4 rig service, report, control, insert, and policy. And E2AP has procedures you see for rig indication, rig subscription, and rig control. Yeah, and then you have also some IDs. For instance, you see rig request ID identifies which rig is coming, RAN function ID, rig action ID. So you have many identifiers that are used similar to what we have also in 3GPP. So to summarize this service model, the service model exposes the information of a specific RAN function over E2 interface. And this is what makes E2AP extendable, because we can actually add more and more service model. E2SM information is embedded within E2AP procedures as a raw byte. And it is the service model that has the semantic to interpret the data. So E2AP itself does not have any semantic to interpret the service model. So the xApp must know the semantic of the service model. E2AP does not know the semantic of the service model because E2AP is just a container to transport. So the service model knows the semantic of this service model, and xApp must know it in order to decode and understand. Okay, with this introduction, I try also to explain now one concrete implementation that we did and how it could help you for your research. So FlexRig is a flexible RAN intelligent controller, is the evolution of what we implemented back then in 2014, FlexRAN, which was essentially SDN controller for the 4G type of base station. And FlexRig is the next generation of FlexRAN. So if we go back to the architecture of ORAN, essentially we have a E2 agent here in the DU, FlexRig E2 agent. We have another agent in the CUUP, another agent in the CUCP. Here in the rig, we have the FlexRig controller. We also have the agent for the 4G. So FlexRig also supports 4G. You can actually run it with the OAI 4G base station. You can also run it with the SRS 4G base station. So in that sense, it supports both multi-RAT, 4G and 5G, and multi-vendor SRS and OAI. And this is essentially what ORAN wants to do. They are saying that E2 is a multi-vendor interface, which actually you see the example here. So the principle for which we actually started to implement FlexRig are the following. So we went into 5G and we try to understand what is the principles of the design of the 5G so that we can get inspired by the design of the 5G. So in 5G, one of the main features is forward compatibility and extendability. You want to be forward compatible for the scenarios you are not considering today or you cannot imagine. So that is one of the principles we applied. Lean and efficient design, so zero overhead principles, which is a C++ principles, well-known principles, is that you don't pay for what you don't need. So in that sense, all the service model that we develop, they are like a plugin. If you need a service model, you plug it into the rig. If you don't need it, you take it out. So you don't pay for service model that you actually don't need. If you compare with other implementation, this is not the case. In other implementation, the service models are actually embedded in the rig. So you need to pay the whole price for the whole rig. And the reason we took this zero overhead because we foresee the scenarios where you need a rig which has a minimum footprint, like a drone scenario. You need a rig that is very small in the footprint. Low coupling, so there is actually, we don't use any libraries in the FlexRig. Everything is implemented, so no dependency, except for ASN1 and flat buffer. So design features, we implement ORAN E2AP. We have a static and dynamic polymorphism in the implementation, plugin, as I said, and minimal yet very complete API. And there is also, I put the reference to the paper in case you want to know more about the about FlexRig. So this was the FlexRig SDK version 0.1 that we did last year. It has the E2AP protocol. We implemented 20 messages out of 26, which is much larger than any other rig provider. We implemented MAC, RLC, and PDCP service models. Also near real-time rig and the E2 agent. We also can provide these xAPPs. So xAPPs is opposite of the xApp. xApp means external application. xAPP means internal application. So it means that you can also inside the rig embed some application that are much faster for low latency scenarios than the xApp, because the moment you go to the xApp, you are outside of the rig. So you need to pay for some communication between the rig and that external application. In iApps, you don't pay that price of the communication. So you see here the design we have, for instance, OAI LTE, OAI NR. We have the agent library that could come on both of them, and then you have a server library. It could interact with the ORAN compliant rig, or it could also interact with the Flex rig. So both are possible. And then on the top, we also define the xApp SDK. So there is one SDK, software development kit, which helps you to set up the E2AP related protocol. And there is another SDK which helps you to set up the xApp iApp framework. So these are decoupled from each other. This had approximately 10,000 line of codes, and it was very optimized for low latency or resource restricted use cases. In version 0.2, we reached to 50K line of code. So it was a lot of development we did from the version 0.1 to version 0.2. So Flex Rig has become multi-X. So multi-X in the sense that it supports multi-vendor already by design. We actually showed this concept in the OI workshop. Multi-RAT, also multi-language. So essentially here you can have xApps that are coming with different languages, Golang, Java, or Python. Even JavaScript, we can do JavaScript. We use a well-known framework, Swig. Maybe some of you know Swig. So we use Swig to have it multi-language, multi-agent, and multi, of course, xApp. So we also developed two new service models. So one is a slice control, E2SM slice control for Mac scheduling, and the other one, traffic control, which is E2SM TC, which is more for the packet processing at the CU. The same as a switch is gonna do, we actually implemented those functionality in the CU. So you have 6-stage pipeline to process the packet. And one innovation we believe that is very nice and we want to interact with ORAN is this protocol E42. So E42 that you see is a new protocol between the xApp and the rig. So ORAN today does not specify how the xApp are gonna communicate with the rig. We don't know, it is open. So what we did here, we said E2 is already specified. Maybe we can use E2 also for rig to xApp. So we leverage E2, we call it E42. We add few missing pieces, and this E42 actually is the mirror of the E2 that you have on the southbound. So we use the protocol of the southbound, extend it a little bit, and use it between the rig and the xApp. And this we would like to actually promote this. The latency that we are receiving here, I will show you later. We have a latency of below 100 microseconds from the agent library up to the xApp, which is very well suited for real-time control. All right. So one word about the E2SM slicing control. So what we did is that we have a E2 control procedures that I showed you. So E2 control procedure has been implemented. We have an add a slice. So we add a slice in the Mac scheduler. So a slice means allocating certain number of resource blocks to a given slice, right? Second, you can modify. So you can modify the amount of resources, but also you can associate a UE to a slice. You could say, I have, let's say, a certain number of PRB. I take chunk of them, and I associate some users to that chunk. And I take another chunk, I associate other users to that, right? And then you can also delete this slice. So essentially, you manage your resource blocks, right? You can also, it's not implemented yet, we can also change the slice scheduling. So we have NVS implemented today. We want to also implement EDF, earliest deadline first. So we can also have some slice scheduling, how these slices are scheduled among themselves. So you also get, through the E2 report procedures, you also get the slice statistic. So you get number of slices, scheduling algorithm, parameter for each slice, and the number of connected UEs, associated slice for each UE. So you get the number of statistics through the report and the control. So here you see the example of run function, which is the MAC scheduling, service model description, right? And how the xAPP actually interact with the run function. So this was a demo that we showed in OAI workshop. So we had FlexRig on the left side. We had here SRS 4G, and here we had the OAI 5G connected through FlexRig. And here we performed some slicing on the resource block that you see here on a screenshot of the window we had there. And essentially you have some data that actually all of have this rig implemented. So it means that you cannot have this rig on a small device, right? So the placement also depends on the resources that you need. If your use case is resource constrained, maybe you want to place it in the drone, maybe closer to these devices. If it is like a real carrier grade or private networking, it's not clear that the placement, but you need to also consider the placement with respect to the xAPP too.
The xAPP is communicating with one rig, because you said, okay, can be, and usually you suppose that will be there are needs for communication between the rigs. There are data that could be through the X. Okay, thank you.
Okay. Okay, so how much time do I have actually? When is the lunch? 20 minutes ago. So what should I do? How much time? 15 minutes. 15 minutes. All right, all right. Okay, so this was about the slicing service model. Another service model that we believe is very important is the traffic control, TC. The same TC that you have also in a Linux, right? You want to control the traffic. Here our TC is composed of 6 stages. It is located between the SDAP and the PDCP layer. So you have a classifier. So this classifier, you can do deep packet inspection also, DPI. You have a policer, you have a queuing system, a scheduler, a shaper, and the pacer, which actually you see it's located between SDAP and the PDCP. So our dream and what we are targeting, actually this work we already did it, still under review, but we want to treat data flows as the first citizen in the 5G network. Today, they are not treated as a first citizen. The data flows that are coming in the SDAP, but there is no queuing system to manage them as a flow, not as a PDU, right? As a flow. The same that as one switch, SDN switch can do. So for that purpose, we actually implemented, so this is a run function for you. So this run function that we implemented contains a lot of functions. Is one big run function, manages the whole traffic in the 5G and 4G. Through the service model, the xAPP could configure the parameters per flow from the xAPP. This is a service model, E2SM. It's a service model that actually the capabilities are exposed through the service model, and xAPP could actually configure, say, for my flow, I want this type of shaper, this type of pacer. Is lost? No, this is the service model we implemented ourselves. Today, what is standardized is the RAN control RC, or RAN specifies RC, which is more related to the slicing that we had before. They have KPM, key performance monitoring, they have a network interface, but they have not defined the proper traffic control. No, no one. And we have very, very promising results, extremely promising. I don't know if you know the buffer bloat problem. Buffer bloat. Buffer bloat. So the buffer bloat is the scenario where you are playing a game and there are some background traffic that is coming that kills your user experience, right? And you don't have any means to segregate the traffic, right? Through this classifier and this queuing system, you actually could segregate the traffic, make sure that that user that is playing the game, his experience is still smooth, while the others actually is getting the performance they are having. And and this problem of buffer bloat is a real problem in 5G still today. So in terms of some comparison, I give you some few results. So here there are some examples of the round trip time. We compare it with the ORAN implementation and our implementation. So we actually gain a lot in terms of the round trip time for different packet size. So this is we try to characterize the E2AP protocol, assuming that there are large number of packets happening in the E2 protocol between the E2 node and the RIC. And also here you see the Docker image size of Flex RIC versus ORAN RIC. So we are ultra lean. We are really, the footprint is extremely minimal with the same functionality, if not more. So this, you see and this is in terms of the normalized CPU usage of the Flex RIC compared to the ORAN RIC. So we actually really try to make sure that this RIC is ultra lean. And you see that from our perspective, we were foreseeing some low latency and resource constrained use case in the future, for which heavy RIC is not a solution. We cannot put a complete RIC with a Kubernetes cluster for a small type of use case. Even for a small private 5G, you don't need a big Kubernetes cluster to deploy. It doesn't mean that this cannot be containerized. And you see it is containerized already here. This is a Docker image size of Flex RIC. You can automate the whole deployment, but you don't have, let's say, a lot of functionalities that you don't need, essentially. Okay, some comparison that we made between the ORAN RIC, ONOS RIC, and the Flex RIC. It's more quantitative. So this principle of the zero overhead that I mentioned, encoding and decoding, we support ASN1, that is the standard specifies ASN1. We also support flat buffer and plain, which is there is no encoding and decoding. And for the simple reason that we noticed that with flat buffers, you reach much lower latency, the result we showed previously. E2AP version, we are falling behind, but that is not the issue. We need to go to the version 2.0. In terms of the messages, we implemented 20 out of 26. So we implemented a lot of procedures in Flex RIC. Multi-language, yes. For E2 node, ORAN RIC supports Radisys. ONOS, they have OAI, SRS, and Radisys. And we also have OAI, SRS, and also Amerisoft support here. Memory footprint, so we are reducing by more than 75% the memory footprint. The latency, you see, we are very low, very low. And the service model, as I said, they are pluggable and extendable. This, we don't need to go here. So in summary, it proved to us, and also some of the partners very valuable tool for research work, and especially a lot of partners, they are considering FlexRig for future scenarios as well. We have one fancy functionalities I did not explain here, but in the paper it is explained. It is a recursion. How many of you knows FlowWiser? FlowWiser. So FlowWiser, the idea of FlowWiser was to, in a recursive manner, you put one controller on the top of the controller and you go forward. And the reason is that you want to have a specialized controller. You want to separate the concerns. You don't want to have just one controller. So through this E42, which is a simple protocol, we also have this recursion. So you can recursively create controllers, one on the top of another. So one controller is specialized for AI ML, another controller is specialized for traffic control, another controller is specialized for the resource allocation. So you can actually separate these service models and have a specialized control. Okay, maybe I answer a little bit the question of Irfan here with the xAPP. So this is the xAPP definition according to the ORAN. In the standard, you find this definition. An application designed to run on the near real-time rig, and it will consume some of the data that are coming. The application is independent of the rig and may provide by any third party. The E2 node enables the direct associations between the xAPP and the RAN functionality. As we said, those red lines. So the xAPP is gonna control the RAN functions through this specified service model. So however, ORAN has some limitations. Not defined interface for the xAPP interface. This is not specified. It's up to platform providers. And most common solution, as I said, is gRPC. And this xAPP still needs to have this concept of E2 node and not define the semantic of onboarding, how we can onboard an xAPP into the rig. So because rig needs to know what are the xAPPs that are onboarded to this rig in order to give them the association ID, in order to manage them, and also manage the conflict across different xAPPs. This is not actually defined. So that's why we decided to enhance E2 with E42 with 5 new messages. We have E42 setup request, setup response, subscription, request, subscription, delete, and control request. So these are extensions similar to the E2 to E42. I don't go through this because of the time, but the process is very standard. So as I said, multi-language and okay, here is some of the results we obtained, and with that I will stop the presentation. From the E2 agent to the xAPP latency. So you want to receive a report or you want to send a control command. On the left-hand side, this is the 1 gig Ethernet link between E2 agent, rig, and the xAPP. On the right is the 25 gig network interface. So this uses the local interface, right, to interact xAPP to the rig to the agent. This one uses the real NIC 25 gig, right? And you see here we have 1 E2 node, 2 E2 node, 3 E2 node. I cannot actually read here. So E2 agent to FlexRig latency, and this is FlexRig to xAPP. So this is one part of the delay, and this is another part of the delay. And here the values are in microseconds. So here we see from E2 agent to FlexRig, we have somehow below 200 microsecond delay. And when you go actually to 25 gig, the delays are even better than local host because of course the interface has more bandwidth, right? So here we are below 100 microseconds in 25 gig between the E2 agent and the rig in a multi-machine scenario, not a single machine, multi-machine scenario. And again, when we check from FlexRig to the xAPP, We see that here we also have 200. There is one case where we have 400, and we actually resolved this. There was some logging problem, but as you see, the results of the latency is very promising, allowing to perform report and the control on a sub-millisecond level, which is actually very, very good. Very good. I don't think I go here anymore. Let me see if there is anything I want to tell you. No, I think summary. So FlexRig is the ORAN compliant E2 standard. It provides flexibility because FlexRig is flexible rig. So we wanted to make sure it is flexible actually. So we have this extendability through this plugin service model and this zero overhead concept that you don't get extra overhead for the things you actually don't need. We implemented many procedures, and here I put you few links. We presented FlexRig in Mobile World Congress 2021. This is a link for the video. Service model implementation tutorial and FlexRig repository, in case you want to try. And with that, I think I'm done. Any question before lunch? You're okay? Yes.
The setup you showed us targets radio resource management. Is that correct?
The service model, you mean?
Yes.
So one of them is the scenario we have today. One is monitoring of MAC, RLC, PDCP, and RRC. That is one. The other one is the slicing control, like allocating resource blocks. And the other one is a traffic control. These are the three service model we are targeting.
Yeah, I would like to target the RRC part, which is essentially for procedures like handovers and like handovers. And I would like to ask if the latencies that you mentioned could be increased by cases of handovering where you need to generate messages from the RRC layer.
No, that are very fast. I had some results. I will share the slide that ASN encoding and decoding are very, very fast. No.
Okay.
You don't really get any, you don't perceive it.
Okay.
Still you can be below 1 millisecond. But for handover, you don't need that, by the way. Yeah.
I have a question.
Oh, sure.
So you mentioned something about xAPPs and xAPPs.
Yes.
And what's the granularity in the control of the base station that we can achieve with the xAPPs? Would that be sub-millisecond or?
Yeah, that is actually even faster than the xAPP because you don't pay for E42.
Okay, so that
You
thing is
bypass the
bottleneck.
complete northbound. You are embedded inside the rig.
And the rig would be co-located, for example, with a base station or something like that. So that
It could be that rig is co-located with the base station, or it could be that the rig is somewhere else, but xAPP co-located with the rig.
Okay.
It's basically, we consider this because we had this concept in FlexRAN 2. I don't know if you remember.
Yes.
So the idea is to make sure that if you have something very, very critical, you can still use the API, internal API, CAPIs.
Yes,
to
exactly.
go faster.
So that,
Yeah.
yeah. Thank you.
Yeah. I think we are ready for lunch.